Everyone, I'm Raj, fourth year aerospace engineering student at University in London.
And hi, as Naomi said, I'm Matthew, a recently graduated aeronautical engineer from the University of Sydney. So what is the project? Now this is what astronomers want. This is a $2.5 billion Hubble telescope, and these are CubeSats. Now the term AstroSats from our title is a term that's been given to vehicles that can perform space-based astronomy from a CubeSat. So I suppose, what is a CubeSat? CubeSats are lower cost, lower risk platforms that take advantage of commercial off-the-shelf technology and a standard bus design to increase access to space. Now their platform, or this CubeSat, can be stacked in multiple predefined locations to increase the size of the vehicle to be able to host larger or more complex payloads. Now the scientific community was asked the question, what astronomy mission would you like to perform from a CubeSat platform? Now, submissions to this answer were taken, and a workshop was held in December to decide, as a community, what would be Australia's next space-based astronomy mission. A decision based off well-justified science and the viability of the mission. As this question was posed primarily at the science community, it was our role to aid this discussion, selection, and development process by providing engineering assistance as the missions developed.
In other words, this project comprises 3 phases: a pre-workshop, the workshop, and a post-workshop. In the pre-workshop phase, we analyze the selected mission based on CubeSat limitations or critical parameters such as target orbits, power, mass, and size. This was done using a high to low risk matrix. I have a sample here just in case anyone wanted to have a look later on. So, we provided assistance to the science and technical audience of the Australian astronomical community present at the workshop. At the workshop, the scientists presented their sciences and objectives. Working groups were then formed to down select the mission, and it is important to highlight based well-justified science and the viability of the mission. Yep. So these are the outcomes of the mission: 2 optical-based and 1 radar-based mission.
So we took those and we entered a design process. Now the design methodology was the same for all 3 projects you saw on the previous page. The science objectives were provided by the scientists. The science requirements were determined by working with the scientists. And finally, the engineering requirements were developed from the science requirements. Now, this process of science objective dictating science requirement, which define the engineering requirement, is a good design practice. Throughout the design evolution, continual reference will be made to these identified requirements to ensure the mission's success. The above example for a space high cadence wide field ultraviolet telescope, which is proposed by Brad at the back, has currently not been progressed further past this point based on time and available resources. However, from just the above definition of the mission, it can be seen that there are no obvious deal breakers and that the project is feasible to fit in a 3 to 6 unit CubeSat. So 3 to 6 unit would be 3 or 6 of these stacked. The other 2 projects were transitioned through a conceptual design phase, the results of which will be presented to you today.
The Huntsman Space Eye. Now, imagine the number of things you can do with UV astronomy, from the composition and temperatures of hot young stars to the evolution of galaxies at their very beginning and the late stages. Isn't that just wonderful? What else? Observation of faint, distant objects, amongst others. But there's a problem here on Earth, though. The ozone layer blocks or absorbs most of those wonderful lights at about 35 kilometers, hence unreachable to the ground-based telescope. Many think that balloons might solve the problem, but unfortunately this is not entirely true because of the scattered light from bright sources such as the sun and Earth reflection itself. The solution is the Huntsman Space Eye, a space-based telescope by Lee Spittler and Anthony Paulson. So at the workshop, they presented their science objectives and requirements as follows. So they asked to view to view the distant faint objects in the U and NUV bands for a mission duration of about 6 months. So they wanted to observe a single target, continuously observe a single target near the celestial pole. They highlighted that they need to be located away from the scattered lights and galactic disk, and they wanted about 7 images per orbit. So to do this, we had to generate the engineering requirements. So a minimum altitude of about 35 kilometers was needed to be above ozone layer, and as I said, because it's not a balloon mission, so we need to be in orbit, so above 160 kilometers is a minimum requirement. So the next one will be an image sensor that can deliver and do all the sensors required in the UV spectral range. A minimum aperture of 90 millimeters for the telescope, equipped with deployable buffers and tubes is recommended. A pointing accuracy of about 10 arcseconds to the telescope axis, and a pointing stability of about 0.1 arcsecond for to be able to view the point of sky that they wanted. And also the data rate is expected to be about 0.3 megabits per second. The image sensor is expected to achieve passive cooling. Finally, the minimum power needed for storage and generation for at least 6 months is required. So now, choosing the sensor was quite fun. Took a while to figure out whether we needed CMOS or CCD. CMOS is a complementary metal oxide semiconductor. CCD, as many of you might already know, a charge coupled device. So why we opted for CMOS at the end was simply for these simple reasons, because it consumes less power, it comprises smaller pixels, hence the need for shorter focal length for the optical design and smaller data storage. It is also not prone to radiation damage. And how it works, that's a short video there outlining how it works. The payload, so CMOS BSI, so backside illuminated sensor equipped with AR, anti-reflection coating, and surface preservation treatment was recommended. So low mass, low power. This sensor was an important factor for the design of the optical system, hence in our case a refracting telescope with minimum aperture of 90 millimeters and requiring just about 4 kg, so kilograms, including the sensor itself, and a size that would just fit in half of a 6-tube CubeSat platform. So before I go there, so this deployable refracting telescope here is proving quite hard to mechanically design it, because this is quite risky and complex itself. As you can see there, is a CMOS sensor, and that's the sensor. The orbit. Now, the orbit is a near circular 469 kilometer orbit, based off SCK, System Tool Design Kit, and orbit design software. So it is good to know that it is 16 cycles, or about 90 minutes per day. So based on that 16 cycles per day, the first subsystem was designed, the command and data handling subsystem. So if you can recall back, the scientists required about 7 images per orbit. That makes about 112 if you do the math. 112 images per day, or an equivalent of 336 megabytes of data that has to be transferred per day and stored. So to transfer those data to Earth, and assuming a 10-minute communication, ground communication time, off-the-shelf 2.4 gigahertz S-band transmitter that can allow up to 2 megabits per second of data rate was chosen. The attitude determination and control is an important subsystem for this mission because it deals with an accurate pointing stability of 0.1 arcsecond. So to do that, an MAI 400 off-the-shelf again was chosen. It comes in a package comprising 3 reaction wheels, 3 magnetometers, and 3 torque rods. The temperature range of the selected orbit inside a CubeSat would be around between -17 degrees and 49 degrees. So it is important to note that for the entire system to function normally, it needs to have sort of the temperature has to be between -25 and 80 degrees. So that's the limit of the operating temperature of every sort of component in that CubeSat. So this proves that passive cooling along with a small TEC, the thermoelectric cooling device for the image sensor, would just work fine. And with the electrical power system, 2 off-the-shelf body-mounted side solar panels were chosen. So that would be bathed in the sun during cyclical days, and lithium polymer batteries for observation during cyclical nights or eclipses would be used. So this table here shows how this whole CubeSat would only be about 5.6 kilograms of weight and fitting easily in a 6U CubeSat platform, requiring just about 12.5 watts of power. So further, it is good to know that with the solar panels, we have a margin of about 26.5 watts of power that can be used in case of any malfunction. So this proves that the Huntsman Space Eye would work just fine, and it's a viable mission with well-justified sciences. Thank you.
So the second analyzed mission was a radio astronomy ionospheric correction mission for Mervyn Lynch, who is someone in Curtin University. And the important thing to note on this slide is that this is a radio astronomy mission, whereas the previous other 2 proposed missions were both optical. Now, for a bit of background, ionospheric turbulent electron structure plays the parallel role in radio astronomy that atmospheric turbulence does integrating optical astronomy. Now, with billions of dollars being invested around the world in projects such as the low frequency array, in the Netherlands, a long wavelength away in New Mexico, and the Murchison Whitefield Array, which is a square kilometre array low precursor site in WA, better characterization of the ionosphere over these sites is required for high fidelity results. Now, Faraday rotation is the problem, as it corrupts the incoming signals that these arrays are interested in. Now, Faraday rotation is where the plane of polarization rotates when the wave interacts with a magnetic field such as the Earth's. The important thing to determine is how much it rotates, which is dependent on the frequency you're at, and something called the total electron count, amongst other things. And the total electron count is a measurement of electron density along a path through the ionosphere, or the electron column. Now, problem number 2 is that the electron density changes on a daily, yearly, and solar cycle. Measuring the total electron count currently is done using the GPS network, which operates at around 1.5 gigahertz, but fidelity is lost at this frequency, and other unknown interactions occur at the desired 80 to 300 megahertz range. Now, the animation on the right is a Bureau of Meteorology's GPS total electron count over a 3-day period sampled at 2 hours per second. So the animation shows that how dynamic this environment that we're trying to work in is, and why it's such a problem. Now, the science objectives of this mission would be to determine accurately Faraday rotation, determine radio astronomical source polarization, and accurate measurement of the ionospheric total electron count. As with previous missions, the science objectives lead to the development of the science requirements, which for this mission is the signal frequency, beacon orientation, the type of orbit, duration, and the measurement regularity. To achieve these science requirements, the engineering requirements were determined, and as seen on the table, these requirements spell out the details inevitably required for the mission's success. The details all need to be answered for. The mission is going to be successful. So my solution was for a 3-unit CubeSat to orbit at a 35-degree inclination and 800-kilometre altitude for a minimum of a year. passing over the MWA site regularly, both day and night, transmitting the known beacon signal as it passes over. Now, a 2-day sample mission can be seen to show the vehicle passing over the MWA site 4 times a day, with a variation of around 7 hours from first to last pass. With each completed pass, the vehicle's orbit shifts, and over a 60-ish day period, this shift will progress around the entire globe. Now, the real beauty about this particular orbit is that it services other sites or partners of interest without the need for a second vehicle. So these include the LWA site in New Mexico and the other SKA site in South Africa. This potentially opens up pathways for collaboration and increased funding, which is always a good thing. So the vehicle design. The vehicle's size is expected to be a 3-inch CubeSat, which is sized to fit all the subsystems it requires. The vehicle will likely be piggyback launched to orbit, where it will then transition to a vertical orientation, as seen, at the desired altitude. A boom will be deployed from 2 orthogonal sides, which is not seen. I'll come out there and there. And they're expected to be between 50 and 80 centimeters in length and only a couple of centimeters in diameter. Now, these booms, they will each contain the 3 antenna beacons, so the 3 different signals, that will be deployed to a predetermined rigid state from the stowed state using a tape measure style mechanism that in reverse. The vehicle will maintain this orientation by means of a magnetic controlled coil or rod to control the vehicle, ensuring that that orthogonal plane always transmits down to the sites of interest. Now, the entire power budget is expected to be less than 4 watts per orbit, with the generation abilities to be around the 10 to 11 watts for that particular orbit and inclination. Now, due to the slow natural decay of this size vehicle or this particular orbit, the vehicle will need to be fitted with an end-of-life strategy. So a mechanism similar to Sabre Astronautics' drag-end tether, which is a point mass and string which interacts with the Earth's atmosphere and drags the vehicle down in a 2 to 3 week period, has been sized and fitted in this type of a vehicle, and the mass and size is well within the limits. And something interesting about this particular mission, so stemming from the 2013-2014 internship that we're doing a couple of years ago, was the identification of a mission similar in science goals to the mission proposed by MERV. The variation in the mission, so proposed by Professor Frank Briggs, who is an ANU guy up here, also wants to understand the interaction the ionosphere has on these low-frequency waves, but also wants to directly calibrate the Murchison Wide Field Array, so be a source of calibration. The calibration can be seen, and it's an immediate, shorter-term result when compared to the previous study of the ionosphere model. So this means that this is quicker. Now, Frank also identified that a vehicle at 400 kilometers, so instead of 800 kilometers, would be above about 75% of the electron column. An altitude, he says, is sufficient to correct the sum of the disturbances, meaning that the vehicle could be deployed from the International Space Station, which is at 435 kilometers. So this means that this could be cheaper. The only foreseen engineering variations between this one and the one proposed by MERV is that the vehicle's beam, sorry, for this one, the beam and power signature need to be constant and known during calibration instances. So this requirement isn't necessarily different from the first mission, it's that this isn't required for the first mission to be successful. So this means that we could use the same vehicle. So whilst this type of orbit mission would not fully encompass the full known ionosphere structure, this could be a lower risk, lower cost stepping stone which leads into the bigger 800-kilometer mission. Something to ponder.
The work continues. These projects are an ongoing work, so as we finish with our internship, these works are expected to be continued in collaboration with AICC technical staff in a detailed design comprising detailed costs, estimates and risk to hopefully see them launch one day and eventually fly in outer space.
So just a few thanks first up to ANU and AICC for hosting us here, to our supervisor Naomi Mathers for putting up with us, for the relevant scientists that we had interactions with for their help, and finally to Northrop Grumman for their financial assistance for letting us do this internship. Thank you.
So I've been fortunate to some of the questions, so I'm handing it over to the floor.
Thank you. So the operating temperature of the Hansen space mine, that sounds almost like room temperature. what I wonder is what's the temperature of the CMOS sensor going to be?
So the operating temperature for it to work is below 38 degrees Celsius. You mean the Hansen detector?
The detector, the CMOS detector.
Yeah, so it would be below 38 for it to work. The operating temperature.
Below 38 degrees Celsius.
Yes.
Oh, and that's okay. And that's not going to produce much noise, is it?
Well, it might produce some noise, but we're using a TSC just to cool it down. So hopefully it won't be having a lot of noise problems there.
I was really curious about the concept of distribution objectives. So it sounds like there's a natural quote-unquote K lifetime as a function of altitude. Right. So for example, the 35 kilometer one, how long does it take that thing to decay and burn in the atmosphere?
The 35 kilometer?
Yeah.
I'll let it drop straight down. So the higher orbit one, what are your estimates?
35 kilometers.
Yeah, 35 kilometer.
Yeah, so what are you guys aiming for the
60.
No, 160 will be the bare minimum. So that's where the altitude starts. It's saying like for a balloon, it needs to be above 35 to be able to view in UV light. Yeah.
So the international law is if the natural decay is greater than 25 years, that's when you actually need to have an end of life device to actively remove it from that orbit.
That'll be like it starts to decelerate more up below 160 kilometers because that's where the atmosphere starts with.
A question? Delay?
When you showed the graph in the orbit of the second mission, I didn't quite understand why there was a gap.
So when that's the shift I was talking about. So when the orbit ends, the next starting point is from that point. So it's the way it shifts. So we're kind of making a 3D map on a 2D plane, and it kind of, to continue it on, it shifts. So the vehicle will not pass over Australia for a certain period of time, like so it'll regularly hit Australia, that S shape, and then it will eventually move away, and then it will come back around and hit it a few more times again.
It's the way the software shows the Earth rotation underneath the orbit.
Yeah.
It's a graphical anomaly.
I've got a question for each of them, but I'll start with Raj. You mentioned that the CMOS sensor was quite mechanically risky. And so my question then is...
Just to clarify that, it was the optical design that would be mechanically risky.
Okay, sure. So for the optical design, and the same applies, I'm curious about what has been done previously in order to mitigate risks. And the kind of related question is, why did you go to CMOS versus CCD because of that aspect so risky?
I mean, the CCD and the CMOS is not a risky one. The design of the optical, so the telescope, the deployable telescope would be a risky one because it's a deployable one, so it has sort of, it's a hard structure, so it might just break or something might not work mechanically in that, so it might be risky for the whole mission. Yeah.
So just to fill in on that, why do you need to deploy it? Why won't a system work within the 3U length of the CubeSat?
It can be done, but this saves a lot of weight, especially with CubeSat. It's a good thing to save weight. And also, having less weight is...
So longer focal length, fewer, therefore less weight, basically.
Yep.
I think that was one of the original specifications was the focal length, so that's one option. But the question is whether the AAO or whoever does some work on some folded optics. And so this is very much a conceptual phase.
So then my other question kind of related to that is, I really like how you identified a complementary mission that has helped mitigate some of those risks. Given that, what would you consider to be the key technical risk for that particular mission? What's the thing that would keep you up at night?
That's the thing. I don't see if there is one. I don't see why this hasn't already been thrown out the side of the ISS and already used to calibrate this array. Where, I mean, I don't know the science behind how much it will benefit, so maybe this is the problem, but I mean, scientist says it benefits. I think that engineeringly there isn't any challenges that's stopping it from happening, and it can quite easily be done. I think maybe the boom deploys, making sure that happens, but that's nothing new. It's been done before. And
I'd probably add it's probably more about building political confidence than it is about technical risk.
So yet again, that isn't an engineering challenge.
I came partway through your talk, so maybe this question's irrelevant, but the, with the rotation measure mapping of the ionosphere, you do certain different passes over the MWA side every 7 hours. How quickly does the ionosphere vary?
Okay, so you might have missed that then. There was a particular slide that shows the ionosphere, or the electron density in the ionosphere is continually changing. So it will change on a daily basis, on a yearly basis, and on a solar 11-year cycle basis. So the scientist, Mervis, is interested in that kind of 1-year time frame. So he wants to regularly go over every day to capture the variations each day, and he wants to have it up there a long enough time to capture the variations over a full year. So this here is a 3-day animation sampled at 2 hours per second. So the hot spot that comes down with this density increase is at the peak of the day. Normally at early afternoon is when it really starts to peak, and then towards the night, so we're in the middle of the day, and then it starts to shift back at night, and the density changes. So, I mean, we're seeing variations from, just on this map, between, say, 75 and 15 TEC units, which is 10 to the 16 electrons per meter squared. So it changes a lot. How much that actually influences the science, I'm not sure, and that's not my role to work out.
Well, people doing aperture synthesis observations, you know, they've got 12 hours to, you know, do a synthesis. So if it varies more quickly than 12 hours, then, and that's been my impression that, in fact, it does, and that's what degrades aperture synthesis observations.
Yeah, so it definitely does.
But they're trying to map out the annual cycles just so that they know what the range is, rather than trying to calibrate individual observations.
So I know when Frank was talking about the possibility of calibrating the Murchison, the aspirational sort of objective would be to have a permanent platform, but this is not that. So there's different.
It's all just about building up that understanding of this, seeing how it changes and modelling. So that's what the first mission was proposed, that kind of building up the knowledge.
Well, thank you very much.
Thank you for that grilling.